Okay, everybody. So one of the things that we've been having a lot of trouble with is understanding the difference between distance and displacement. So I made a little question here for you. So we're looking at velocity of a particle moving along the x-axis. So it's doing is it's just sliding back and forth. So here's my particle. It's sliding to the left and the right along that x-axis. And its velocity is given by that s or sine of t squared over 10. And we're talking about the interval from 0 to 8. So first question, how far is the particle from where it began? So when we start to look at how far it is from where it began, now we're talking about displacement. Okay, what is its displacement? Well, its displacement, let's see. So I went ahead and I graphed this thing. And you'll notice I have a bunch of stuff over on the left, but this green graph is that v of t function. And you'll notice when I put it into my GeoGebra, I use x's instead of t's. But according to this, it looks like that graph is positive until just over 5.5. And then it looks like it's negative between 5.5 and just short of 8. And then it looks like it's positive again. But we're worried about the interval going from 0 to 8. So according to what we know about relating graphs together, whenever the derivative, in this case, the velocity function, is positive, so in this vicinity between 0 and 5.5, then that position should be increasing. Whenever the derivative is negative, in this case, the velocity being the derivative of position, so between that 5.604 number and that 7.926 number, the velocity is negative. So that must mean the position is decreasing. So that would tell me that this particle that is sliding along our x-axis, that blue x-axis right there, is going to slide to the right for a while because the velocity is positive, and then it's going to slide back to the left. Well, based on looking at that graph, it looks like it's not going to get back to where it started because the area in between 0 and that 5.6 looks bigger to me than the area between that 5.6 and that 8. So I hypothesized that this thing is going to start at some number. It's going to go to the right for a while. It's going to come back to the left, but it's not going to get all the way back to where it began. Okay, so now let's answer the question. So the question says, how far is the particle from where it began? Well, if I want to find my displacement is always going to be area under the velocity curve in this case. So the v of t, or an area change in function, is area under its derivatives curve. And we're using velocity and position here as an example. So I'm going to want the integral going from 0 to 8 of that v of t dt. And I'm going to punch it in, and I already have it ready to go on my calculator. So if I punch that in, you'll notice there's my shaded area. It's given by 1.365. So how far is this particle from where it began? It is going to end up at 1.365 units away from where it began. So its displacement, it went to the right for a while. It came back to the left. It ended up 1.365 units from where it began. Okay, so let's shift gears now. What about part B? How far did the particle travel from 0 to 8? How far did it go? Well, now we're talking about distance traveled. And when we're talking about distance traveled, that is area. Okay, let's spell that right. Area under the absolute value of the v of t equation. Or in some people are going to call that speed. So let's go back and let's look at our example. So I'm going to unshade the displacement there. So there's my velocity curve. And again, what we said was, hey, if I asked you really quick at t equals 4, what is the function's velocity or the particle's velocity? It looks like it's, I go to that point, its velocity is about 1, right? At 3.96, it looks like its velocity is about 1. Well, what if I said, what's its velocity at just short of 7? Well, it looks like that velocity would be -1. Well, that means, remember velocity, all that means is a sign on it. It means it's going backwards. Okay, well, what if I asked you for the speed? Well, when velocity is positive, the speed would match the velocity. But when we start talking about the speed at a point like, for example, that one right there, the speed, we'd have to change the sign on it because speed has to be positive. So I'm going to make a quick little adjustment right here. So this one is now, I just graphed the absolute value of that velocity curve. So I'm going to turn velocity off for just a second. So now I'm looking at the speed curve, and all I did is I took the velocity, which was negative between about 5.5 and about 8, and I flipped it up. So now, let's say I asked you for what the speed was at t equals 7. Well, that looks like -1, but if I come up here to about that same place, that speed looks like it's going to be 1, right? So when we talk about speed, we're not going to have a direction. We're just talking about how fast we're going. So now let's go back and answer our question. So for part B, how far did the particle travel from t equals 0 to t equals 8? That is going to be the area I want to know, because now when I look at this, if I'm looking at just the red graph and not the green one, well, according to that, the area between 0 and that 5.6 number, well, that's going to give us a positive result. Well, so is the result going from now, the red going from that 5.6 to that 7.9. So if I want to find how far did the particle travel, well, that would be the integral from 0 to 8 of the absolute value of that v of t equation. And that's going to be the area under that speed curve. Area under that speed curve, if I want to punch that in there, that looks like it's 4.303. So we've got, what does that mean? Well, the green one, remember, the green one was telling us, it was including a sign. So the green one was saying, hey, you know what? We're going to go up for a while. The particle's going to go to the right along the x-axis for a while, and then it's going to come back to the left. But the red one says, all right, if I really want to know exactly how far that is, take the sign off of the velocity and include just the speed. That's going to say it's going to go so many units to the right, and then it's going back. When it goes back to the left, we're going to add those units on, and that's going to make a total distance traveled of 4.303. Okay, last question. If the particle was at x equals 4 when t equals 0, so again, remember the particle, so let's say that on that blue thing that we're looking at right there, let's say that that particle at time 0 was at x equals 4. What is the position of the particle at t equals 8? So now we're going to introduce another formula to you, and that formula I'm going to introduce is start plus change is equal to finish. The starting value would be x equals 4 when t equals 0. So x of 0. My finishing value, I want to know where this thing is at t equals 8. So I want to know its x position at t equals 8. I want the change then is going to be the area under its derivatives curve. So that is, now I'm going to go back to green. That is going to be the integral from 0 to 8 of my v of t dt. Because again, we want displacement now because we want to know what its final position is. Well, we already did, and you can see it on the screen up there. We already did our displacement. That was 1.365. My original position was given to be x equals 4. Put those two things together. Where is it at t equals 8? It's going to end up being equal to, or at 5.365 is going to be the x position at t equals 8. And that makes sense because what we said, when we're looking at that x-axis, if it started at 4, we said our velocity was positive for a while, and it was going to go to the right for a while. That particle is going to move to the right for a while, and then the velocity was going to turn negative, and it was going to come back. Well, where it ended up then was at that final position of about 5.365 after it made that change. That's distance versus displacement, and then our favorite little formula right here, start plus change equals finish.